Okay, so hello and welcome everyone. This is the eighth week of the interactive live sessions for the course Computational Fluid Dynamics for Incompressible Flows. So as you all know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. Now, week 8, if you have seen the lectures, they have all been about the stream function vorticity formulation. So, our we will through questions and answers, we will be discussing that topic itself. So, without any further ado, let's jump into question number 1, which is asking us the primary purpose of using the stream function vorticity formulation in CFD. What is the reason why this particular formulation is used? Is it to option A, simplify the Navier-Stokes equations? Is it to option B, to improve the numerical stability? Is it option C, to conserve mass and momentum? Or is it option D, to reduce the computational time? So, I'm sure you're all familiar with the format of doing things. So once you figure out the correct solution after reading the question carefully, you can type in your answer in the chat box, or you can unmute and answer as well. And if you feel like if you have any doubt regarding the question or anything else related to the uh, topics that which we are discussing, please don't hesitate to ask. Just go ahead. Okay. So we already have a quick response in favor of option A to simplify the Navier-Stokes equations. Let's see what others have to say. And yeah, participating in these questions are absolutely mandatory. Okay, we have another response in favor of option A. Any other responses? What is the primary use of the stream function vorticity formulation in CFD? Does it simplify the Navier-Stokes equations? Does it improve numerical stability? Does it conserve mass and momentum? Or does it reduce the computational time? Okay, so let's have a look at the solution. So, as you all said, it is actually option A to simplify the Navier-Stokes equations. How it happens is that what is the Navier-Stokes equations? If I write down quickly, then it's the continuity equation dou u dou x plus dou v dou y equal to 0 for incompressible 2D flow, by the way, and steady as well. So even if we do not consider steady, the arguments hold true, but we will consider steady for now. And u dou x, v dou u dou y equal to minus 1 by rho dou p dou x plus nu into, I'll just write in shorthand, uh, nabla square u and Laplacian of u basically. Similarly, the this is the x momentum equation. Similarly, there will be a y momentum equation as well, which is u dou v dou x plus v dou v dou y equal to minus 1 by rho dou p dou y, and again nu into graph square of v. This is the y momentum equation. So basically, if we look at the whole thing, then we have three variables, three unknowns basically, and three equations. The variables are what? They're u, v, and uh, p, the pressure, the two velocity components and pressure, and three equations as we wrote here. And once we convert this into the stream function vorticity formulation, what happens is that it boils down to only two unknowns and two equations. What are those? The two variables are stream function and the vorticity. And there are two equations as we saw in the lectures as well. So for the sake of repetition, I'll write them down. So one is the Laplacian of stream function becoming equal to minus of vorticity, and there is a vorticity transport equation as well, which looks something like this. This is the convective part. There are no sources, only uh, the diffusive part. Right. So yeah, so the entire system of three unknowns and three variables and three equations boils down to only uh, two unknowns and two equations, or two variables and two equations. So this is how it simplifies stuff. Okay. I hope the idea is clear. Any questions on this? If you have any questions, please don't hesitate. All right. So we will move on. We'll move on to question number 2, which is asking us, in the context of stream function vorticity formulation, what does the stream function represent? Does it represent the velocity components of the fluid flow? Does it represent the rate of change of vorticity in the flow? Does it represent the streamline patterns of the fluid flow? Or does it represent the density distribution within the fluid? Okay, we have got two very quick responses in favor of option C. Let's see what others have to say. Option C, the streamline patterns of the fluid flow. What does the stream function represent? Is it option A, the velocity components of the fluid flow? Option B, the rate of change of vorticity in the fluid? Option C, the streamline patterns of the fluid flow? Or is it option D, the density distribution within the fluid? We have a couple of responses telling us that it should be the streamline patterns of the fluid flow. It's a simple one, so let's have a look at the solution. It is indeed option C, the streamline patterns of the fluid flow. So this brings us to another question. It's a simple one. If you're familiar with fluid mechanics, I'm sure you should have this knowledge. What a streamline is, let me ask you this. I want any one of you to answer. What is a streamline actually? What does it mean? How is it useful? You can say anything. You can either unmute and speak up, or you can type in the chat box if you feel more comfortable that way as well. Basic things. What is a streamline? Flow in a particular direction following a particular path. Exactly. So basically, uh, uh, the textbook definition of streamline is, it's a line, an imaginary line, in which at every point, if you take the tangent to it, that represents the velocity of the fluid at that point. So if I take this point and take a tangent, it will be this way, like this. And if I join all those points together, then that forms one streamline. Now there are multiple streamlines. So what happens is that, since at every point the flow velocity is tangent to it, there is no component of velocity perpendicular to it. It's entirely tangential to that. this does not exist, only along this. So if I draw multiple streamlines, there is no fluid which can cross these streamlines. Or if I take this, let's say I start off with this volume of fluid which I'm shading. Okay, so this packet of fluid can never exit these two streamlines. It can get distorted or something, like it can get deformed as it flows, but the mass of the fluid, so to say, remains within that. So it's as if the streamlines are impenetrable walls through which through which any fluid cannot escape. So this becomes really useful in visualizing flows. So in experimental settings, in experiments actually, if the flow is unsteady, then visualizing streamlines would be very difficult. Streak lines, on the other hand, are much more easier to visualize. So but in steady case, we know that streamlines, streak lines, and path lines, they all coincide with each other. So in steady cases, streak lines are actually equal to streamlines. So experimentally, also we can visualize these streamlines which show what the velocity field should look like, because we know that along the line we know that the velocity of the fluid is along the tangent at that point, as well as we know that these packets of fluids, they travel in between adjacent streamlines. They can't escape through through either of them. So it's a useful tool for visualizing fluid flows. And in the stream function vorticity formulation, we actually directly find out the stream functions. So iso stream function lines are again stream lines, right? So along these stream lines, the stream function are actually equal to some constants. So we can call streamlines as iso stream function lines, just like isotherms in heat transfer, right? So in a, let's say in a domain, I know the values of stream functions at all points, and if I just simply connect the points with a line which have the same stream function value, I will then get streamlines directly. Whereas in case of the uh, what is it called? It's called a primitive variables approach when I solve for UVP directly. Primitive variables, where I'm solving for U, V, and P directly from the Navier-Stokes equations. That's called a primitive variables solution. In that case, I can find out U and V at each point and then try to find out the streamlines by drawing, uh, you know, by joining points uh, tangent to whom the velocity is at those points. So this is a more of an indirect approach, whereas in the stream function vorticity formulation, I get the stream function as a function of space, as well as it could be time as well, but that doesn't matter. In a steady case, it would be just space. So from that, I can simply join the lines with the same value of psi, and then I will get these streamlines, and that will help me visualize the fluid flow in a much more physical sense. Okay, so that was all about streamlines. I've been ranting on for a while now. If you have any questions, please don't hesitate to ask. Any questions on this? Okay, so let's move along to question number 3, which is asking us, in the stream function vorticity formulation, what does the vorticity represent? Is it the rate of change of velocity? Is it the curl of the velocity field? Is it the divergence of the velocity field? Or is it option D, the magnitude of the velocity field? So mathematically, these can be represented as the rate of change of velocity. So let's say dou u, not dou, d dt, or yeah, or in a isolated way also it can be dou u dou t. The curl of the velocity field is simply nabla cross omega, which is a vector by the way, or no, not omega, of the velocity field. So u, is it the divergence, which is a dot product, or is it simply the magnitude of the velocity? So if u is the velocity, then these are the mathematical ways in which these options can be represented. Which of them represent vorticity? Okay, we have two quick responses, both in favor of option B, telling us that it should be the curl of the velocity field. Let's see what others have to say. Okay, we have another response in favor of option B. Let's have a look at the solution. It is actually option B, the curl of the velocity field. So I'll write again. The omega is actually curl of the, sorry, curl of the velocity field. And what it physically means is that, uh, if I take a packet of fluid like this, and this is my coordinate system, x and y. So if there is angular rotation of this element, I'll draw some lines in between as well so that we can represent it better. So if it rotates about its center of axis while translating, so you can imagine, right? This packet of fluid is translating, and while translating, it's rotating as well. So if this packet rotates by some angle, and there is a rate of that rotation as well. So the rate of rotation of a packet of fluid, that is actually what vorticity represents. And in a 2D scenario, we are only worried about the z component of the vorticity, which is equal to uh, dou u dou y minus dou v dou x. Right? Did I do this correctly? Let me check. It could be negative of that as well. I j k dou dou u dou dou v dou dou, sorry, dou dou x dou dou y dou dou z and u v z. I don't have z in case of a 2D flow, so the kth component would be dou v dou x minus dou u dou y. Okay, sorry, so this should be negative of that. That's what I was suspecting. Okay, so quick check. That should be dou v dou x minus dou u dou y. Any questions on this? Vorticity again is important in you know engineering applications of CFD as well as academic applications, because let's say if we are trying to find out, so let's imagine there is a very complicated flow system. I'm drawing a simple one, but in reality we are often worried about things like this, or let's say some airfoil, which is vastly used in aerospace applications. So there, it's the rotation of the fluid components which happens only in presence of viscosity. In inviscid flows, we know that vorticity is zero, and this generation of vorticity is actually uh, very important, because that's where viscous dissipation takes place. And viscous dissipation is important. Why? Because viscous dissipation is what leads to you know uh, hydraulic losses, we know about losses, right? So those hydraulic losses are caused due to viscous dissipation, and viscous dissipation is more in regions where the vorticity is more. So in different domains, we actually try to find out where the uh, vorticities are higher, because that's where eddy currents are being produced, and the momentum gets destroyed in those regions. So in this context, you can imagine that there would be some vortices formed here and the vorticity would be high there, and that would be a source of a loss. Am I making sense? Like, if you have any questions related to this, please ask. Everyone knows what hydraulic losses are, right? Yeah. So from a design perspective, we can always, check where the vorticity is high, and then we can make adjustments to our design so that those regions can tackle the fluid flow better. And yes, so in relation to flow separation, not in a direct way, but if the flow separates, then the vorticity in those separated wake regions would be higher. But then again, flow separation is a different issue. There, the concept of for laminar flow and for turbulent flow, separation is different, and then there are the question of adverse pressure gradient, which comes into account. Reasons are different, but what happens as a result of it is a high vorticity region, which causes a lot of losses. So in many design cases, we need to mitigate them, and in many research cases, we just need to understand the flow physics better through visualizing vorticity. There are many importances of vorticity in that sense. Okay. All right. So let's move along. We'll move on to question number 4. This is a very simple question. It's asking us, what is the mathematical equation that relates the stream function to the velocity field? So this is just simply how psi is related to u or v. Is it option A, u equal to dou psi dou y and v equal to minus dou psi dou x? Is it option B, u equal to dou psi dou x and v equal to minus dou psi dou y? Is it option C, u equal to dou v dou y and v equal to dou u dou x? Or is it option D, u equal to dou u dou x and v equal to dou u dou y? Sorry, these are wrong. These should be something else. Anyway, you just type in the chat box when you have figured out the correct answer to this. So as you can see, option C and D are already wrong because they don't relate with psi in any way. The only thing is whether, okay, so anyway, I won't waste any time on this. You guys have already figured out that it's option A. So let's look at the solution. It's actually option A. So U is actually the y gradient of psi, and V is the negative of x gradient. Now, many different textbooks use a different sign convention as well. It could be U equal to minus dou psi dou y and V equal to dou psi dou x as well. So this is also correct and this is also correct, but any one of them. You can't have both positive or both negative. There would be one positive and the other one should be negative, and u should be the y derivative and v should be the x derivative. These are the two rules you have to keep in mind. Okay. I guess there are no questions on this. If you have, please don't hesitate. Okay. We will move along. We'll move on to question number 5 now. Okay, so this is now coming to the way in which stream function vorticity formulation is executed. So while executing it, how is the vorticity calculated? Is it done by taking the gradient of the stream function? Is it done by taking the curl of the velocity? Is it done by taking the divergence of the velocity? Or is it calculated by taking the Laplacian of the stream function? In the stream function vorticity formulation, like the way in which we solve it for fluid flow cases. How is the vorticity calculated? Read the question carefully, and once you have figured out the answer, you can type it in the chat box, or you can unmute and ask as well. Unmute and answer as well. So mathematically, I'll write down each of these options where, so by taking the gradient of the stream function, by taking curl of the velocity field, by taking divergence of the velocity, or by taking the Laplacian of the stream function. How is vorticity calculated? In the stream function vorticity formulation. I've written the mathematical forms of the options, which are written in words, of course. If you have any doubts, you can always ask. Okay, so we have one response in favor of option D, that is by taking the Laplacian of the stream function. So let's have a look at the solution. Okay, so we got another response in favor of option D, and that is indeed the correct one. So if we remember the stream function vorticity formulation, omega is calculated as minus dou square psi dou x square plus minus dou square psi dou y square, which is nothing but the Laplacian of the stream function. Negative of it, obviously, but that's how it's calculated. Now, where the confusion may arise is that by definition, omega is the curl of velocity, but that's not how it is found in the stream function vorticity formulation, because u is something that we want to find out. That's one of the unknowns that we are solving for. So we can't really, we don't really know u so that we can take curl of it and find out the vorticity. Then there won't be any need of doing this in the first place. Only thing we have is the boundary conditions and the equations which we know, which we derived for the stream function vorticity formulation. We solve them iteratively until we arrive at a solution where I know the stream function in the entire domain as well as the omega in the entire domain. Then from this we can find out what u, v as well as what p is. The primitive variables. These are known as the primitive variables. And psi and omega are sort of derivatives, sort of derived variables. Anyway, any questions on this? It was simple enough. I hope I could make things clear. Anyway, moving along, we'll move on to question number 6. Now, this is regarding the boundary conditions. So, how does the stream function vorticity formulation handle boundary conditions? Is it option A, it automatically satisfies all boundary conditions? Is it option B, it requires additional boundary conditions beyond those that are given for the velocity field? Is it option C, it does not require any boundary conditions? Or is it option D, it only requires boundary conditions for the vorticity field, that is omega? So which one should it be? Read the question carefully. If you have any doubt, you can ask. And if you have figured out the solution, you can type in the chat box or you can unmute and answer as well. How does the stream function vorticity formulation handle boundary conditions? Is it option A, that it automatically satisfies all boundary conditions? Is it option B, that it requires additional boundary conditions beyond those which are given for the velocity field? Is it option C, it does not require any boundary conditions? Or is it option D, it only requires boundary conditions which are for the vorticity field and nothing else? Which one should it be? A, B, C, or D? What happened? No guesses, anyone? Okay. We have one in favor of option C telling us that it does not require any boundary conditions. It's self-sufficient. Atmanirbhar. Okay, so let's have a look at the solution. It actually does require boundary conditions. It's not that it doesn't require. And those are beyond those which are given for the velocity field. So let's say if I have a square domain like this, and I tell you that at all the walls, u and v are equal to 0. Let's say u equal to v equal to 0. Thing is, if you are using the stream function vorticity formulation, then you need to convert all these boundary conditions given in terms of u and v into the terms of psi and omega at all the boundaries. So turns out if u is 0 in the vertical walls, then dou psi dou y is 0, and if v is 0 on the horizontal walls, then dou psi dou x is 0. From this, the value of psi can be calculated, some constant, some constant. And then that is how all the uh, uh, boundary values of the stream function psi is found out. And similarly, you have to find out those values for omega as well. How that is done is we already know that omega is equal to minus of Laplacian of psi. If we know the value of psi at all the boundaries, then we can find out those values for omega as well. There are some simplifications, some little mathematical trickeries involved, but the bigger picture is that it requires boundary conditions and it requires them in terms of psi and omega. So if you give me the boundary conditions in terms of u and v, I have to convert them into psi and omega, and then only I can proceed and try to solve using the stream function vorticity formulation. Okay, I hope that makes things clear. Any questions on this? If you have any doubts, please get them cleared right now. Okay, so if there are no questions, we'll move on to question number 7, which is asking us how is pressure calculated in stream function vorticity formulation? Is it by using Bernoulli's equation, by using the pressure Poisson equation, by using Euler's equation, or simply pressure cannot be calculated in stream function vorticity equation? It's just impossible to calculate pressure. Which one is it? Option A, B, C, or D? Okay, we have one quick response in favor of option B, by using the pressure Poisson equation. Let's see what others have to say. So basically, if I formulate, a fluid flow problem, usually what happens is I need the velocity and the pressure fields in a domain. But in this case, I am only solving for psi and omega, right? Using them, I can find out the velocities. Those are easy to find out. Simply u equal to dou psi dou y and v equal to minus dou psi dou x I can put in. After I know psi, I can get u and v that way. But what about pressure? Is it calculated using Bernoulli's equation? Is it calculated using the pressure Poisson equation? Is it calculated using the Euler's equation? Or pressure simply cannot be calculated in this form of solution? So let's have a look at the solution. It's actually option B, by using the pressure Poisson equation. If I remember correctly, it looks something like this. The Laplacian of P equal to 2 rho into the second derivative of psi with respect to x multiplied by again second derivative with respect to y minus a mixed derivative with respect to both x and y whole squared. I'm not entirely sure about this. You can go and check. I think this is the one. So if you remember correctly, we start with the Navier-Stokes equations, right, which look something like this. The convective term equal to minus dou p dou x. There is of course 1 by rho here, and we have plus mu, the Laplacian of u, and similarly the convective term u dou v dou x plus v dou v dou y minus 1 by rho, then dou p dou y plus nu into nabla v. So if I call this equation 1 and equation 2, how we got the vorticity transport equation was simply by eliminating p out of this. So there is dou p dou x and dou p dou y here. So I simply take y derivative of equation 1 and subtract the x derivative of equation 2 from it. That's how we ended up getting the vorticity transport equation, right? And of course, we replace all the dou u dou x, sorry, all the dou v dou x minus dou u dou y with omega in this. That's how we get the vorticity transport equation. This is the important step where p is eliminated from the equation, and this is the primary reason why the stream function vorticity formulation is simpler than the Navier-Stokes equation, because this is where one of the variables is eliminated. So we started off with three variables, that is u, v, and p. Since we are eliminating p, we are boiling down to only two variables from now on. This is what allows the solution of stream function vorticity formulation. But if I now simply, instead of doing this, what we did here, if we simply take the x derivative of 1 and add it with the y derivative of 2, then only, and with some mathematical manipulations, we will get this pressure Poisson equation, where the Laplacian of p, which is nothing but dou 2p dou x2 plus dou 2p, sorry, plus dou 2p dou y2, and we replace all the u and v's with the appropriate gradients of psi. Then we get this equation. So in the stream function vorticity formulation, we get the solutions of psi, right, as well as omega, but we know the solution of psi ultimately, and this is what we can plug in here and then get the value of pressure. So if I have all the values of psi in a particular domain, I can use them to find out what the pressure would be at different points in the domain. So by solving this pressure Poisson equation, at the end we can simply extract out the uh, pressure field in the flow domain. Any questions on this? This might be a little complicated, but things are pretty simple at its core. Any questions? All right, so we'll move on to question number 8. Okay, so this is asking us, can the stream function vorticity formulation be used for 3D flow fields, three-dimensional flow fields? Is it option A? Yes, but it requires the use of vector calculus to formulate the equations. Is it option B? Yes, but it is a general formulation that can be used for both 2D as well as 3D flows. It's a general formulation. Or is it option C? No, it is only valid for certain types of flow fields, such as only laminar or only steady state flows. Is it option D? No, it can only be used for 2D flows. It can be used for 2D flows only, and it can't be used for 3D flows. Okay, so we have a response in favor of option B, telling us that it's a general formulation that can be used for both 2D as well as 3D flows. Let's see what others have to say. Read the question carefully, and once you have figured out the correct option, you can type in the chat box. Alright, so let's have a look at the solution. So it's actually option A. It can be done, but it needs the use of vector calculus to formulate the equations. So basically, stream function in a 2D scenario is very simple to visualize, right? So simply u equal to dou psi, dou y, and v equal to minus dou psi dou x. That's it in 2D. But once you go to 3D, things become a bit complicated. There also a stream function psi can be defined, but it's a bit more, uh, what can I say, complicated. So it's usually, we know that at every point, dou psi should point in a way that it should, uh, the velocity should be along it. So the differential along x should be proportional to u. Its difference along y should be proportional to v, and its difference along z should be proportional to the w, that is the z component of the velocity. And that's how we can get the psi vector, which is psi x I cap plus psi y j cap plus psi z k cap. This is a vector, and the omega is also similarly. So these are vectors now. This is also omega x I cap plus omega y j cap plus omega z k cap. It can be formulated, but the entire vector calculus of it is very complicated. And on top of that, so the main interesting thing here. So in a 2D case, we showed earlier, right, that we converted a three variable, three equation system down to a two variable, two equation system, right? So we had uh, u, v, and p over here. We had boiled it down to only psi and omega in this. So this was an advantage of using stream function vorticity instead of velocity and pressure. Now, what happens in 3D is that we start off with a four variable, four equation space, right? So the continuity equation and the three momentum equations: x momentum, y momentum, z momentum, right? So the four variables over here are u, v, w, the three velocity components, and pressure, obviously. Now, if I go to this mode, then I have six variables because psi has three components: psi x, psi y, psi z, and omega also has three components: omega x, omega y, and omega z. So now I am looking at 6 variables and I need 6 equations as well to solve them. So psi x, psi y, psi z, and omega x, omega y, omega z. So in 3D, things do not get simplified. Instead, they get more complicated. So it's not useful to apply this to 3D problems. Okay, here was the interesting part. Any questions on this? Any questions, doubts, remarks, anything? Did you understand this? What is happening here? Like when we move from 2D to 3D, what happens? Why is it not useful anymore? It's not only complicated but useless as well. So there's no point of doing it. All right. So let's move on now to question number 9, which is a very simple question. It's asking us which dimensionless number appears in the non-dimensionalized form of the stream function vorticity equations. So from u, v, psi, omega, if we move to u star, v star, psi star, omega star, the non-dimensional quantities, then in those equations, which dimensionless number appears? Non-dimensionalization, I'm sure all of you are familiar with. So let's say there is a velocity scale capital U, then U star can be represented like this. V star can also be represented like this. Sorry, not V, capital U itself. Psi can be represented, and the length scale is L, let's say. So in that case, it will be UL, and omega star would be omega by u by L. Okay, so we have two responses in favor of option D, the Reynolds number. It's actually correct, Reynolds number it is, because the first equation remains the same, which is omega star or minus omega star equal to uh, dou 2 psi star dou x star squared plus the second derivative in with respect to y star. The another equation, that is the vorticity transport equation, that becomes u star dou omega star dou x star plus v star dou omega star dou y star equal to, instead of nu over here, it becomes 1 by Reynolds number into the Laplacian of omega star, and Laplacian in terms of x star and y star, not x and y. So Reynolds number is the non-dimensional number which appears here, and this is equal to ul by mu, by the way. U is the characteristic velocity scale, L is the characteristic length scale, and nu, as you know, is the uh, dynamic kinematic viscosity of the fluid. Any questions on this? It was a simple one. Okay, so let's move on to the last question of today's session, which is a true or false type of question. So you need to read the statement and figure out whether it's true or false. The statement goes like, for two-dimensional incompressible flows, vorticity stream function formulation is more accurate than velocity pressure formulations. Is it true or false? Okay, so we have one response telling it should be true. Let's see what others have to say. And why? Let me add that. You have to say why true or why false. You can unmute and answer, or you can type in the chat box as well, whichever way you feel comfortable. Some justification. What do you think? Like, what's your thought process going on here? Let's have a look at the solution. It's actually true, and the reason lies in the fact that we are finding out the psi, the stream function, which is which is related as with velocity as its gradient, right? So u is actually the gradient of psi. And so if we find out psi in a way, so that depends on the numerical discretization, whichever we are using, whether 2-point central difference or 3-point backward difference, that doesn't matter. But let's say we are finding out with some discretization scheme which gives us order n accuracy of psi in psi. Now since u is actually uh, the gradient of psi, that is where dividing it once again by whatever spatial discretization we are on. So that's why the order in which we get the order of accuracy in which we calculate the u and v, that is actually another order higher. So the error is less as compared to some other formulation where u would have been calculated uh, with an accuracy of order n or delta x to the power n. Is the idea clear what I'm trying to say? Any questions on this? Please ask if you are not entirely agreeing with me on this. We are finding out a quantity and then taking a gradient of it to find the other quantity. So psi is the thing which we are solving for first, and then from psi we are going to u, which is a gradient of this again. So we are dividing it further with another delta x or delta y, whatever. And we are going even finer there. So that's why the order of accuracy is actually higher in case of, in general, higher, given that you are performing similar discretizations on, let's say, the primitive Navier-Stokes equations, or uh, whether you're using the stream function vorticity formulation for doing this. Okay. Any questions on this? If not, we will close our session here today. So it's been a nice session. Thank you all for participating today, and we will meet again next week. Thank you. Bye. Good night.
Sir, hello.